Okay, let's look at the Doppler effect and redshift. Right, if we consider a car like an F1 Formula car, it will be producing an engine noise. Now, I'm afraid I'm going to produce some rather embarrassing sounds now. So we have a car here, and it's producing an engine noise like that sort of sound. That's the pitch it's producing. So if you were inside the car, that's the sound you would hear. Now, because the car is moving towards the left, anyone in front of it would actually have the wavelength shortened. So what the person in the car here is a sound, the person in front of it who is a sound, much higher pitch sound. Okay, so that's why when a car comes towards you, you hear a sound as it goes by. Okay, the wavelength has been shortened in front of the car, and behind the car it's been stretched out. As the car moves away from you, it stretches out the wavelength, so you end up with a longer wavelength behind and a shortened wavelength in front of you. That's where you get the sound of a as the car goes past you. Also, you'll get a sometimes if you hear it like in a war film, you hear a as bombs fly over you. You can hear planes doing the same thing. I do remember there is a video of the Big Bang Theory where one of the characters describes the Doppler effect, and so that might help you. It's a bit of fun. I'm not sure it really explains it entirely. Right, okay. Now we use exactly the same idea with light. Light does the same thing. If we have a light bulb here, let's imagine producing a bit of a red colour here. That's the colour it's pointing. Now if the red light is moving in one direction, in front of it, the wavelength gets shortened. And if the wavelength of red light gets shortened, it actually changes colour. Whereas in the sound, it produced a higher pitched sound. In light, it produces a higher pitched light, which would be in green, for example. It could be anything above red. So red, orange, yellow, green, blue, indigo, violet could be those things there. So it could be producing green light, and if it went particularly fast, it could produce blue light. And if it went even faster still, it would then shift into ultraviolet and so forth, going towards the shorter end of the spectrum. That's as if the light is coming towards you. Okay, if the light is going away from you, just like in the previous case, the wave gets stretched out. It becomes a longer wavelength. And so what you end up with here would be a sort of a darker shade of red, or perhaps even infrared. Okay, so you can see the wavelength appears to change. Now I need to explain colour in a way of something called light spectra. Now a spectroscope is a device which allows light to come through a narrow slit. And when the light comes through this narrow slit, perhaps light from a star, okay, what you do is you get a telescope, you point the telescope towards the star so that the light from the telescope goes through, light from the star goes through the telescope and through a tiny slit, and then it enters a prism, a 60-degree prism like this. And you probably know from our stuff on light that white light can be split into different colours. And if you do this, you end up with different coloured lines. Now those are called spectral lines. Now the reason it isn't the full colour of the rainbow is that different elements of the periodic table give off different colours. Okay, it's almost a bit like a barcode. Different substances produce a different barcode to another. So this here could be the barcode, I don't know, of hydrogen. Two close red lines and a green and a blue. It's not really the case, but that's an example. And it's almost like a fingerprint identifying what the substance is that has sent the light. Okay. Now, when we look at the colours, the red colour and the green colour and the blue colour and the dark red colour, you might get this. So above the central light, you can see there's two red lines there. Now, when you get hydrogen, for example, it produces a very distinctive pair of lines like that. Not necessarily red, but a pair of lines like that, and they're used as markers. And what you find is that as the source moves towards you, those spectral lines get shifted towards the green end and then towards the blue end, and that's been known as blue shift. At the other end, if you go to the right here, you can see that the red lines have been shifted towards the other end, and that'd be the red end of the spectrum. And that's where we get this idea of red shift and blue shift. If you see red shift, the thing is going away from you. If you see blue shift, it's coming towards you. Just imagine how cool that was. If I was able to get a red ball and throw it at you really, really quickly, I could make that red ball appear blue. I'd have to go at stupidly high speeds. It'd be impossible to do it. And then if I got this red ball and threw it away from you, well, what would actually happen is the wavelength would be stretched to such an extent that you wouldn't actually be able to see the red colour. It would now actually be infrared and would be giving off a heat signal. Right, now when we look at all the galaxies out there in the universe, we actually find that 99% of them are red shifted. In other words, they're moving away from us. not only are they all moving away from us, just 1% are coming towards us, but 99% are moving away from us, we can also see that those that are furthest away from us are travelling the fastest away from them because they've got the biggest red shift. And this suggests that the universe is expanding. In fact, scientists say the universe is expanding. And this supports the theory of the Big Bang. Okay, there's a whole video on the Big Bang in a second, but there's Doppler effect and redshift.